Over the weekend of July 11th, 2014, crews successfully relocated the historic Puyallup River Bridge along State Route 167, about 60 feet to the east. Originally built in the 1920s, the bridge was moved to make way for the construction of a new, modern structure that will better serve current traffic demands. The move was a complex engineering feat, requiring careful planning to preserve the bridge while clearing space for the replacement. The relocated bridge will temporarily carry northbound traffic during construction. This project is a key part of improving safety and mobility in the Puyallup area. Bridge demolished and rebuilt during 2 intensive 54-hour rail possessions. Ten gas, water, and electric utility cables were safely diverted ahead of bridge installation. A 250-ton crane was used to lift and position heavy precast units with precision and efficiency. Seven 5-ton precast concrete beams installed for bridge deck. As part of the bridge reconstruction, 2 number 29-ton precast concrete (PCC) parapet units were installed to form the protective edge barriers of the bridge, ensuring both structural integrity and safety for future rail operations. In addition, 16 number 8-ton PCC approach units were carefully positioned at either end of the structure to provide smooth transition zones between the existing railway alignment and the new bridge deck. These units were precision lifted into place using a 250-ton crane and securely fixed, ensuring long-term durability and minimal maintenance requirements post-installation. Approximately 100 meters of new service ducts were installed within the bridge structure to accommodate utility diversions and facilitate future maintenance access. Additionally, 16 heavy PCC containment units, each weighing between 20 and 30 tons, were precisely positioned. Over a 4-month period, a major infrastructure project was successfully completed to replace the aging Killingworth Road Bridge on the Metro line in Newcastle upon Tyne. Originally constructed in 1860, the bridge had long outlived its design life and was no longer fit for modern traffic demands or safety standards. The £5.5 million project required full closure of both the road and the rail line to enable safe and efficient delivery. The scheme involved significant engineering challenges. A total of 60 sheet piles were installed to provide structural support during excavation and construction. Additionally, 50 precast concrete units, weighing a combined 630 tons, were used in the construction process, along with 700 cubic meters of in-situ concrete, which was poured on-site to form key structural elements. At the heart of the project was the installation of a new 370-ton bridge span, which was constructed nearby and then driven into place in a precise and carefully managed operation. This single activity was a highlight for the project team and local stakeholders, taking only about an hour to position the massive span in its final location. Delivered by Story Contracting in collaboration with Nexus, the project was completed on schedule and within budget. It marked the first full bridge replacement in the metro system's history, and now allows for future highway widening beneath the structure. Throughout the project, the team worked closely with local residents, who showed considerable patience during the 34-day railway blockade. Thanks to detailed planning, seamless coordination, and dedicated execution, the new Killingworth Road Bridge is now ready to serve the community for generations to come. As part of Phase 4 of the Northwest Electrification Program, NWEP, significant gauge clearance works were undertaken in a busy residential area to facilitate future electrification and modernization of the route. The scope involved the full demolition and reconstruction of a bridge structure, completed over two 54-hour continuous OROR, on-rail off-rail possessions, ensuring minimal disruption to the rail network while meeting demanding program deadlines. One of the key challenges was operating in a constrained urban environment with limited access and space. This required meticulous logistical planning and coordination. Fiber optic cables critical to local services were supported and suspended in situ to avoid disruption and maintain connectivity throughout the works. A 1,200-ton Kiro rail crane was deployed to install the new structure, which consisted of 11 prefabricated steel girders. These were delivered just in time to mitigate space constraints and avoid prolonged disruption to the surrounding area. Two 30-ton parapet walls, each faced with traditional sandstone to preserve the local architectural character, were also installed with precision. The bridge deck itself, weighing 60 tons, was cast in situ, demanding careful coordination of materials, concrete supply, and working hours within possession windows. The confined site layout and proximity to residential properties required constant stakeholder engagement, noise mitigation strategies, and safe traffic and pedestrian management. Overbridge construction, golf course railway crossing removal. In November 2014, an innovative overbridge construction project was undertaken to eliminate a top 10 high-risk level crossing in North England. To support the bridge, 50 No. 5 T precast concrete (PCC) abutment units were installed. The reinforced earth-retaining walls were built using 25,750 tensor blocks and supported by 5,525 square meters of tensor geogrid earth reinforcement. This advanced geotechnical design provided long-term structural integrity and minimized the environmental impact. Construction also included 236 cubic meters of precast and in-situ concrete, ensuring a robust and durable structure. The modular bridge was installed during two 7-hour ROR, rapid on-rail possessions, using a 200-ton mobile crane, minimizing disruption to railway operations. The site, a golf course split by a railway line, posed a significant safety challenge due to frequent public interface with rail operations. The solution involved constructing an overbridge, the first time a flexi-arc system had ever been used on the railway. This project not only removed a major safety hazard by separating rail and public access, but also won the UK Rail Industry Award for Outstanding Project. It set a precedent in railway construction with the use of flexi-arc technology, offering enhanced durability and reduced installation time. The overbridge has significantly improved safety for the golf course users while maintaining railway operational efficiency. De Westrandweg A5 is een circa 10 kilometer lange autosnelweg die het knooppunt Raasdorp met de A ten zuiden van de Koentunnel in Amsterdam verbindt. Het viaductdeel van ruim 3 kilometers lengte maakt hiermee de eerste dubbeldeksweg van Nederland mogelijk. Het ontwerp- en bouwcontract voor de Westrandweg werd uitgevoerd door de combinatie Westpoort, bestaande uit Van Hattem en Blankenvoort, KWS Infra en Boskalis. De contractvorm was Design and Construct, waarbij Volker Infradesign zorg droeg voor de detaillering van constructieve onderdelen zoals liggers en pijlers. Voor de viaductdelen over spoor en weg werden prefab PIQ-liggers gebruikt met lengtes tot maar liefst 61,75 meter. De langste prefab betonliggers ooit geproduceerd in Nederland tot dat moment. Ze werden aangebracht met een speciaal ontwikkelde launching-girder die het mogelijk maakte de liggers langs spoortrajecten of langs andere infrastructuur te schuiven zonder tijdelijke kolomconstructies. De koppeling van prefablokken en hun plaatsing verliep volgens een zorgvuldig faseschema. Bij knooppunt Raasdorp vond de montage van liggers plaats in 4 weekenden in de herfst van 2011, telkens van vrijdagavond tot zondagochtend, om dagelijkse verkeershinder zoveel mogelijk te beperken. Gedurende die nachten was 1 rijstrook per richting beschikbaar op de A9. Over de N200 gebeurde de plaatsing over enkele nachten in september, met verkeersregelaars en lichtmasten voor korte stops en regeling van verkeersstromen. De inzet van de launching girder zorgde voor minimale trillingen tijdens heiwerkzaamheden, wat hinder voor spoorverkeer en lokale omwonenden aanzienlijk verminderde. Bij brugdelen boven het spoor zijn deze vooraf naast het spoor opgebouwd en vervolgens tijdens een weekend ingeschoven of gedraaid. Een constructie die op deze schaal voor het eerst werd toegepast in Nederland. De Westrandweg werd in december 2012 in gebruik genomen, gelijktijdig met de Tweede Koentunnel. Het viaduct vormt sindsdien een belangrijke ontsluitingsroute voor het westelijk havengebied en de noordelijke Randstad. The Gotthard-based tunnel in Switzerland, the world's longest railway tunnel at 57 kilometers, features a state-of-the-art slab track system, Festefarbahn, designed for high-speed and heavy freight traffic. Unlike traditional ballasted tracks, this system offers long-term stability, precision, and reduced maintenance, ideal for tunnel conditions. The rail installation process in the Gotthard-based tunnel is a high-precision operation that plays a central role in enabling safe and efficient high-speed rail travel. The installation begins with the transportation of 120-meter-long rail segments into the tunnel. These rails are drawn into position using a custom-designed rail pulling unit mounted on a crawler chassis, allowing for precise maneuvering in the confined tunnel space. Each rail weighs over 7 tons, and the positioning must be accurate to within millimeters. Once positioned, the rail ends are aligned for welding. Using a flash butt welding machine, the rail ends are clamped and joined under high pressure with electric current until the steel reaches fusion temperature. This ensures a seamless rail joint capable of withstanding speeds of up to 250 kilometers per hour. After welding, the joint is cooled and inspected, and the rail is then lifted from the transport rollers and placed onto precisely aligned rail holders. To maintain the required track geometry, teams work simultaneously on several tasks. While one crew welds the rails, another prepares the next section for installation. The rail installation machine continues moving forward along the already laid track, laying the next rail segments in sequence. Each track section is adjusted in height and alignment, using reference points embedded in the tunnel. The rails are later fixed onto pre-positioned concrete sleeper blocks using specialized equipment. This entire process is executed in a continuous workflow, ensuring both speed and accuracy, with teams covering up to 200 meters per shift. The placement of sleeper blocks in the Gotthard-based tunnel is a highly automated and precise process. Prefabricated concrete sleeper blocks, each engineered to exact specifications, are delivered into the tunnel on specialized transport wagons. A portal crane equipped with a laying beam positions up to 60 blocks at a time between the rails. Each block must be aligned with millimeter precision to ensure proper track geometry. Workers verify the exact position of each block, ensuring tight contact with the tunnel base. This precise foundation is critical for the later steps of rail fastening and concrete embedding, ensuring long-term stability and safety. Track construction in the Gotthard-based tunnel involves the seamless integration of rail installation, sleeper block placement, and alignment into a continuous, high-precision process. After the sleeper blocks are placed, the rails are positioned on top and roughly aligned. A specialized track-laying machine then adjusts the rails to their exact horizontal and vertical positions using laser-guided measurements and reference points embedded in the tunnel. The rails are fixed temporarily, and the precise geometry of the track, such as gauge, elevation, and cant, is fine-tuned to meet strict tolerances, often within a millimeter. The track alignment is continuously monitored by surveyors using high-accuracy instruments. Once the correct geometry is confirmed, the rails are fastened to the sleeper blocks using elastic clips. This process ensures stability, reduces vibration, and allows for long-term durability under high-speed traffic. The construction teams work in overlapping shifts to maintain continuous progress, laying up to 200 meters of track per shift. Concrete works in the Gotthard base tunnel are a critical phase of the slab track system, ensuring the permanent fixation and structural integrity of the railway line. After the rails and sleeper blocks are correctly positioned, specially designed concrete trains deliver fresh concrete directly into the tunnel. These trains consist of multiple wagons carrying sand, gravel, cement, water, and additives, up to 500 tons of materials in total. The mixing unit at the front of the train prepares concrete on site, allowing the mix to be adapted in real time to the tunnel's temperature and humidity conditions. The freshly mixed concrete is poured into the space surrounding and beneath the sleeper blocks. Workers use internal vibrators, or vibrating bottles, to compact the concrete thoroughly and eliminate air pockets. Precise compaction is essential to ensure the concrete bonds tightly with the blocks and tunnel base, creating a durable and vibration-resistant slab track. After compaction, the surface of the concrete is manually smoothed. Despite the high level of automation, this finishing step requires skilled craftsmanship to achieve the required cross slope, typically 0.7%, even in straight sections. This slight incline ensures proper drainage of condensation or emergency water. To maintain continuous workflow and quality, the concrete is poured in 2 8-hour shifts. The concrete must harden for at least 48 hours before trains can use the section. Throughout the process, quality inspectors test each batch of concrete for consistency, spreadability, and strength. This ensures long-term durability and performance of the track infrastructure. Final inspection involves precise measurement and quality checks by surveyors and engineers. Every meter of track is examined to ensure compliance with millimeter-level tolerances. Any deviation requires immediate correction. Inspectors verify rail alignment, sleeper positioning, and concrete integrity to ensure the track is ready for safe, high-speed operation. For over 60 years, the Alaskan Way Viaduct loomed above Seattle's waterfront, a double-deck concrete highway that moved traffic through the city but separated its residents from the shoreline. Aging and seismically vulnerable, it posed a serious safety risk, especially in the wake of the 2001 Nisqually earthquake. In response, the state opted for a bold transformation, replacing the viaduct with a deep-bore tunnel and reclaiming the waterfront for public use. Demolition of the viaduct began in February 2019, unfolding in carefully planned phases. The process was complex. Crews worked just feet from buildings, businesses, and busy city streets, often 60 feet above ground. By September 2019, the final piece of the elevated highway came down, signaling the end of an era. The removal marked more than just the end of an old roadway. It opened up sweeping views of Elliott Bay, reconnected downtown with the water, and made way for a revitalized urban space. The waterfront transformation includes new parks, pedestrian paths, bike lanes, and public spaces that draw people to a once overlooked part of the city. Today, before and after views of the site show a remarkable evolution, from a noisy highway corridor to a vibrant, accessible destination. The teardown of the Alaskan Way Viaduct not only improved safety and mobility, but also reshaped Seattle's relationship with its iconic shoreline, offering a reborn waterfront for future generations. The installation of the first prefabricated concrete segments in the West Island of Montreal marks a key milestone in the advancement of infrastructure work in the region. These concrete segments, manufactured off-site, are transported and precisely assembled to form the arches of the tunnel. This method speeds up the construction process while ensuring consistent quality. The project, located in the West Island, is part of a major development aimed at improving public transit and regional connectivity. This phase represents a shift toward more sustainable and long-lasting infrastructure for the decades to come.